Astronomers announced that our universe is vibrating with gravitational waves measuring light years in length. It isn't one or two waves coming from here and there, but rather many waves reverberating through our universe simultaneously. We first detected gravitational waves way back in 2015 when two relatively small black holes merged. As they spiraled inwards, they generated gravitational waves of increasing frequency until they peaked at around 250 Hz. But the waves detected in this new study have frequencies that are so low, they're measured in nanohertz. That's billionths of a hertz. We don't know exactly where they're coming from yet, but it's thought that most of them are probably due to supermassive black hole binary systems. In order to detect gravitational waves that are light years long, you need a detector that's also light years long. So astronomers use an array of pulsars to create a galaxy-sized gravitational wave detector. And if that weren't cool enough, the data also suggests there may be additional waves coming from the Big Bang itself. If that's really the case, then we may be detecting waves coming from inflation or even cosmic strings. As a deadhead, the idea of vibrating cosmic strings immediately made me think of this. So today we're going to break down how the gravitational wave background was detected using a pulsar timing array, why these are not your father's gravitational waves from 2015, and why we may be getting our first glimpse of new physics from the Big Bang. General relativity says that gravity is caused by mass distorting spacetime. But if that mass is accelerating, it can create waves in spacetime as well. Because gravitational waves are ripples in the fabric of spacetime, they don't require any medium to pass through. So they propagate unimpeded at the speed of light, whether it's going through the vacuum of space or through the core of a planet. However, gravity is fundamentally a weak force, so it takes a tremendous amount of mass accelerating very fast to create waves that are just large enough to be detected. And that's why the first detection of waves in 2015 were of two black holes that were merging. As they merged, their waves rippled through the two LIGO detectors in Louisiana and Washington state. LIGO works by reflecting laser beams off mirrors located at the ends of two 4-kilometer tunnels. When a gravitational wave passes through, they move the mirror's position ever so slightly and the laser interferes with itself. By measuring the interference pattern of the laser, you can determine how strong the gravitational wave was and then work backward to figure out what must have caused them. The first detection came from the merger of two black holes weighing 36 and 29 solar masses. And yet, for all of that mass and all of that acceleration, the passing wave nudged the length of LIGO's arms by just 4 times 10 to the minus 16 centimeters, or about 1/200th the radius of a proton. And that was one of the more powerful gravitational wave signals we detected. But all of those detections were possible because they were created by stellar mass black holes that orbit very close to each other, so they produce short wavelength gravitational waves which can be picked up by kilometer-long detectors. But what about binaries consisting of supermassive black holes? Most galaxies have a supermassive black hole in their cores that can range from millions of solar masses to tens of billions of solar masses in the largest galaxies. And galaxies merge all the time, so their supermassive black holes should eventually find each other and form a binary system. But supermassive black holes eventually settle into a stable orbit separated by a few light years. That means they're going to take several years to complete a single orbit. Gravitational waves move at the speed of light, so we're talking about waves that are light years in length. And that means you need a much larger detector with arms measuring tens, hundreds, even thousands of light years. Fortunately, we can use pulsars to create a galaxy-sized gravitational wave detector. Pulsars are rapidly spinning neutron stars, and they form when the core of a massive star collapses. At the moment of collapse, the core weighs over 1.4 solar masses. So it collapses from the size of Mars to the size of Manhattan in just 1/10 of a second. However, a city-sized ball of neutrons more massive than the Sun is really just the start of the weirdness. The star it formed from was already rotating, but when you squeeze that much mass down into such a small size, it has to spin up in order to conserve angular momentum. It's the same reason a figure skater spins up when she pulls in her arms. That fast spin makes neutron stars highly magnetized, so they emit twin beams of radiation out their magnetic poles. When one of those beams sweep along our line of sight, we detect the neutron star as a pulsar. So pulsars are like cosmic lighthouses that rotate several times a second. And that makes them natural clocks because we can detect their pulses with a regular cadence. But the fastest spinning pulsars complete their rotation in just a few milliseconds. And these so-called millisecond pulsars can spin up to hundreds of times each second. That makes millisecond pulsars extremely stable with accuracies approaching that of atomic clocks. That means you can take one of these pulsars and predict the arrival time of a particular tick several years before it arrives, and you'd still be accurate to within 1/10,000,000th of a second. So if a gravitational wave were to pass by, it would alternately stretch and compress space-time at right angles to the wave's motion. And that in turn would cause the time of arrival of the pulses to alternate between arriving later and earlier than normal. Of course, space is three-dimensional, so it will oscillate in multiple directions at once as the wave passes through. Now, these gravitational waves are light years in length, so the timing variations of each pulsar takes years to complete as well. But even then, you wouldn't detect very much. The gravitational wave from a supermassive black hole binary might move spacetime by 1 part in 10 to the 15. To put that into perspective, one of the closest pulsars in the study is 0.63 kiloparsecs, or 2,035 light-years away. But a gravitational wave from supermassive black holes might move the pulsar back and forth by just 20 kilometers. So we need to detect a difference of just 20 kilometers across 2,000 light-years of space over a multi-year period. However, during that time, a lot of things can go wrong with our pulsar clock. Starquakes can cause sudden changes in the pulsar spin. The pulsar might wobble or precess ever so slightly. The pulsar could be part of a binary system, and even the interstellar medium surrounding the pulsar will slow down its light. And yet, despite all of that noise, we need to be able to extract a variation in the pulsar timing on the order of just tens of nanoseconds over many, many years. So to overcome some of those errors, you monitor the signals from several different pulsars spread about the sky. This is called a pulsar timing array. To that end, different collaborations around the world monitor different PTAs for something like the last 20 years or so. So the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, used the Arecibo Radio Telescope in Puerto Rico, and they still use the Green Bank, the Very Large Array, and Chime telescopes today. The European Pulsar Timing Array uses telescopes in Germany, the UK, Netherlands, France, and Italy. The Indian Pulsar Timing Array uses the giant meter wave radio telescopes in Pune. Australia uses the Parkes Radio Telescope for its PTA. And the Chinese Pulsar Timing Array uses the 500-meter aperture spherical telescope, or FAST. All of these collaborations announce the detection of not a single wave coming from a large event, but rather the collective thrum of low-frequency gravitational waves coming from all directions in the universe. This thrum was dubbed the gravitational wave background. But how do they know that all of these changes in pulsar timings were in fact due to gravitational waves and not due to just random noise in the data? Well, it turns out that gravitational waves should produce a particular pattern of changes in the timing delays between different pairs of pulsars. So as the wave passes through, different pulsars will show different timing delays depending on how far apart in the sky they are from each other. This pattern is called the Hellings-Downs correlation. It says that if two pulsars are close to each other in the sky, they tend to have similar timing changes as the gravitational waves pass through. Namely, they'll either both arrive early or they'll both arrive late. But if they're far apart in the sky, the timing changes are less similar. Typically, one arrives early while the other arrives late. So what does the data show? Well, there were several collaborations that worked independently, but they all gave similar results using different sets of pulsars and different analysis techniques. For example, the Nanograv collaboration monitored 68 pulsars over a 15-year period. This plot shows the separation angle between any two pulsar pairings on the horizontal axis and the strength of the correlation on the vertical axis. The black dashed line is the expected Hellingsdown correlation. The blue data points are the binned correlations as measured from 2,211 distinct pairings in the array. As you can see, the match looks pretty good. Not perfect, but very strong. The second plot is what's called a power spectrum, and it plots the excess and the timing delays over different frequencies of gravitational waves. The measured correlation is represented by the blue line surrounded by the shaded region, which represents the uncertainty in the measurements. As you can see, the blue line is passing within the violin gaps of the Hellingsdown's correlations for each frequency. So that's telling us that the pulsar's timing differences are consistent with Hellingsdown's, and therefore appear to be consistent with gravitational waves. But there is something else going on in the Nanograv results that points to something very interesting. Let's go back to this power spectrum. This black dashed line is the pattern of timing correlations you would expect if the background waves were all being caused by supermassive black hole binaries. If that were the case, then the measured correlations in the blue line should match up with this dashed line. They don't. In fact, the higher the frequencies of the gravitational waves, the more the measurements seem to be pulling away from supermassive black holes. So what's going on here? Well, it could just be that we haven't been looking at enough pulsars for long enough, and that eventually the blue line will gradually tilt more toward the black dashed line as we gather more data. But the divergence on the high frequency end is already well outside the current margin of error. So what if it doesn't ever match up? Well, one possibility is that the high frequencies could be hinting at a solution to a problem with supermassive black holes. Namely, these binary systems tend to stabilize their orbits once they close to within a couple of parsecs of each other. After that, there's really no obvious way to get them to merge. And this is something called the final parsec problem because presumably the most massive black holes should have formed from the merger of smaller supermassive black holes. Another possibility is that perhaps these high frequencies were due to some relatively nearby supermassive black hole binaries. Maybe they were so close that there were some otherwise negligible high-frequency overtones that were just loud enough to be detected. The Nanograv team did in fact identify two possible candidates, but they were ultimately rejected because they couldn't find a host galaxy merger that was close enough. So that leaves the door open to the possibility that some of these waves are coming from new physics, in particular the ultra-powerful events that occurred during the Big Bang. For example, during the first 10 to the minus 33 second of creation, the universe would have rapidly inflated by a factor of 10 to the 26. That's 100 trillion times bigger. It's like taking half of a DNA molecule, about 1 nanometer, and expanding it to 10.6 light years in 10 to the minus 32 second. This is the epoch of cosmic inflation. It's when the universe expanded faster than light, and it really put the bang in the Big Bang. So far, inflation is purely theoretical. However, one of the predictions of inflation is that it should have produced gravitational waves that are still resonating throughout the universe today. Another possibility is that the waves are being caused by a sudden phase transition that took place at the end of inflation. Essentially, the universe stopped inflating at super speed and resumed a normal rate of expansion. Perhaps bubbles of space-time expanded and collided with each other at that moment, and maybe we're catching their gravitational waves today. But my favorite idea is that some of these gravitational waves could be due to the vibrations of cosmic strings. In this scenario, the universe would have cooled so quickly that the fabric of space-time became fractured and created a network of whisper-thin strings that hold some of the energy in the Big Bang to this day. These strings would be no thicker than a proton, yet they would stretch across the observable universe. If those strings really exist, they could be vibrating with an ultra-low frequency, creating some of these background gravitational waves. These are exciting possibilities, but they're also very speculative. Still, the nanograph team investigated whether it's possible that new physics might be playing a role here. This is a table of comparisons to the hypothesis that the signals are coming from a combination of supermassive black hole binaries and a form of new physics. Those points are shown in red. And the hypothesis that the signals were coming from new physics alone, shown in blue. The probability of one hypothesis being more correct than the other is represented by something called the Bayes factor. When you get to Bayes factors approaching 100, it's probably a hypothesis worth considering. And sure enough, there are a couple of very high marks here. One is for a model that includes scalar-induced gravitational waves, which I suppose is a kind of inflation-induced gravitational wave. Another is for a model involving cosmic superstrings stretching across the universe. Another interesting point is that if the signals were coming from supermassive black holes, then you'd expect to find them originating from galaxy clusters where there are more mergers taking place, and no signals coming from regions where there aren't any galaxies. The result would be a non-uniform distribution of signals around the sky, or as we call it, anisotropic distribution. On the other hand, if some of the signals were coming from the Big Bang, they'd be coming from everywhere, just like the way the cosmic microwave background is everywhere in the sky. To that end, the nanograph team searched for signs of anisotropy in the data, but they didn't find any. Instead, the data seems to be an isotropic or uniform distribution around the sky. So that clinches it. The gravitational wave background does include new physics, right? Well, no, not at all. Not really. The authors are very clear that all of the tests for new physics are based on many assumptions about supermassive black hole binaries that we honestly don't yet know are correct. They state very clearly that these results are strongly dependent on the modeling assumptions about the cosmic SMBHB population, and at this stage should not be regarded as evidence for new physics. To really know what the GWB is really composed of, we just need to get more data. On the one hand, that means observing more pulsars for longer periods of time, but then again, we don't have to wait another 20 years to make real progress. The current nanograph results were based on their 15-year dataset, but they're currently compiling an 18-year dataset which will likely include stronger signals. And right now, all of the datasets from the American, European, Indian, Australian, and Chinese PTAs are currently being combined into a single International Pulsar Timing Array database. That data release should be ready within the next year or two, with more data coming in after that. So it's likely that in the coming years we'll be able to isolate the first supermassive black hole binary and examine it closely with telescopes. We may even be able to resolve the final Parsec problem. But the most exciting possibility is that we may be able to finally pierce the veil of the cosmic microwave background and directly measure the vibrations of the universe during its first moments of creation. A huge thanks to my Patreon supporters for helping to keep Launch Pad Astronomy going, and a huge shout out to Ben for becoming my newest patron. Until next time, stay curious, my friend.